Hey you, welcome to The Art of Code. My name is Martijn and your brain is about to go poof. Maybe not. But we're gonna make everything you see behind me, and the core of it is really only a few lines of code, so I think that's pretty amazing. If you don't, maybe you want to check out a different kind of video like this one, but if you do, stick around. Alright, so we start out with an empty project. The first thing I'm going to do is I'm going to make a UI element, a raw image element that is going to cover the entire screen. So I have to go here and move this until it fits the entire screen. And let me zoom in a little bit. Also the anchor should move as well to go to the edge so that when I resize the screen, the element resizes with it. The next thing I'm going to do here is I'm going to create a new material. I'm going to call it Mandelbrot, and I'm going to also create a new shader, and in this case I'm going to create an image effect shader because we're going to show the fractal all over the screen as opposed to on a 3D object. So I'm going to go here and call that Mandelbrot as well, and let's open this up. By default, when you create an image effect shader, it puts it in a hidden category, meaning that if I go over here, you cannot see it in this list. So if I go back over here, I have to rename this to something else. And now when I go here, it will be under the right category. So let's assign that. And now let's click here. And my raw image has a material slot over here. I'm going to drag this Mandelbrot material into the material slot. And now let's go back onto the Mandelbrot shader and move that on the side so we can see. And now let's just start by making a Mandelbrot fractal algorithm real quick. I will explain this in a second video in depth, but for now let's just run through it. So I'm going to start with my start position that I'm going to initialize to my UV coordinate. And the second thing I'm going to do is I'm going to add a variable z to keep track of where my pixel is jumping across the screen. And now I'm going to make a loop. And actually before I do that, I have to make a float iter as well that will keep track of which iteration that we're on. So now I'm going to say float iter equals 0, initialize that. Actually, don't say float here because we have it already here. And now I'm going to say iter smaller than my maximum iterations, and I'm going to say iter plus plus. So this is going to make a loop that is the heart of the Mandelbrot algorithm. And then the algorithm itself is actually really simple. So all I have to do is I have to each time update my z value based on my previous z value. And the way to do that is z.x times z.x minus z.y times z.y. And then for the y coordinate, we're going to do 2 times z.x times z.y. And then we have to add our original starting position to that as well. So that is one line of this loop, and the other line is the breakout line. So sometimes we have to break out of the loop, and we have to do that when the length of our z value is larger than 2. And then we just break out of this loop. And then over here, we can just return iter divided by 255. Let's see what that does. And that already gives me a corner of the Mandelbrot fractal. Isn't that amazing? This is only 2 lines of code. Alright, so now what we're going to do is we're going to make it that we can zoom in on this. So right now we're only looking at one little part of the fractal. And by the way, we can already zoom in on this, which is, to me, it's mind-blowing that only a few lines of code can make all of this. But let's make it that we can do this by program. So for that, I'm going to go over here. I'm going to add a variable, call it area, which is going to hold the area that we're going to render. So I'm going to call this area, and it's going to be a vector, which is 4 numbers. And the way I'm going to do this is the first 2 numbers is going to be the center of the area we're going to render. So in this case, let's say 0, 0, which would be the center. And the second, well, actually it would be the center of the fractal. And the second 2 numbers is going to be the size of the area we're going to render, which in this case for the starting position would be 4 and 4. So let's go over here and add this float for area. And now over here we can we have to build our C value based on that area, right? So the first thing would be just to take the position of the area, and then we have to so if this is the position, we have to start a little bit on the left side of that area, and we have to end a little bit on the right side of that area. So for that, we're going to do this. And remember, this UV coordinate goes from 0 to 1, right? 0 to 1. So if I multiply this by 0.5, no, I did that wrong. If I subtract 0.5, now it goes from minus 0.5 to 0.5, and now I have 0 in the middle. And now if I multiply this by my size part of the area, which is the last 2 numbers, right? It's ZW. So the way this goes is, for vectors it goes X, Y, Z, and the last coordinate is called W. So that's why ZW is the last 2 and XY is the first 2 coordinates. So and the last 2 in this case is 4 and 4. So in this case, if my original UV coordinate was, let's say on the left, was 0, then this will go to minus 0.5, and minus 0.5 times 4 is minus 2. And if this is 1, then I have 1 minus 0.5, which is 0.5, times 4 is 2. So this formula here will bring me the original area to minus 2 and 2, which is what we want. So let's see if this works. Okay, so now we have the entire Mandelbrot fractal visible. And now if we go here on our, if we go on our material, we can go here and we can move our fractal around, up and down, and we can also zoom in. Although zooming in is a little bit cumbersome right now because we have to work with 2 variables at once. So let me just put this back, 2 and 2. All right, so let's leave the shader alone for a while and let's create a controller script that can make this a little bit easier for us. So I'm going to right click here, create C# script, and I'm going to say Explorer, and let's look into this. All right, I'm going to get rid of my start here. We don't need that. The first thing we're going to do, let me also get rid of this. The first thing we're going to do is we're going to make a public variable that will hold the material, because we're going to have to change it. So we have to have a reference to it. So let me save that, go over here, and let me add this Explorer script. So I'm on the raw image and I'm going to drag the Explorer script onto the raw image. And then I'm going to drag the material onto the material slot over here. So now we have that. The next thing we're going to do is I'm going to add a public variable, a vector2 for the position, and a float for the scale. And now inside of my update loop here, I'm going to say mat.setVector, and I'm going to set the vector inside of the shader to this new value here that I'm going to create, vector4, and it's going to take pos.x, pos.y, for now let's just say scale, scale. All right, save that, test that. So now I have to press play because I'm just doing stuff in my update loop here. So if I press play, you don't see anything right now, and you might think it's broken, but it's not, because we are just zoomed in too far into our fractal. So over here I can zoom out. And now I can move around as well and zoom in and zoom in any place that I want. Awesome. Now you might ask yourself, well, why did he do two scales here? Why not just have one scale? And the reason why I did that is because there's a problem with this, which is that if well, right now it looks fine because my viewport is square. But if I take this and I move this down, and you see immediately what the problem is that it gets squashed and stretched if my viewport is anything other than square. So we have to compensate for that. And the way I'm going to do that is I'm going to make a float called aspect. That stands for aspect ratio of the screen, which is the width divided by the height. So let's make that the width divided by the height. So screen.width divided by screen.height. And these are integers, so I have to cast them to float, otherwise my aspect ratio is going to be truncated. Float. And now I'm going to make two individual scales, one for x and one for y. So float scale x, and I'm going to just initialize that as the original scale. Scale y equals scale. And now I'm going to use this aspect ratio to change one of these variables based on the size of the viewport. So if I had a viewport that is very wide, so it's much wider than it is high, then what happens here is that this number will be larger than this number. Therefore, my aspect ratio is going to be larger than 1. Okay? So if over here I say aspect is larger than 1, if my aspect ratio is larger than 1, then I need to take proportionally less of the y direction, right? I would see less, like for the y direction, I would see maybe from here to here as opposed to all of this. So what I can do now is I can say scale y. So again, the aspect ratio is larger than 1. Well, if it's larger than 1, I can divide the y scale by the aspect ratio. So that if it is twice as wide as it is high, then this gets scaled down by a factor of 2. All right. On the other side, if I have the other situation where my viewport is a lot higher than it is wide, I need to do the opposite. So now my aspect ratio is smaller than 1, and now I need to change my scale x. So I do scale x, but I can't do divided by aspect here because aspect is smaller than 1. So if you divide by something smaller than 1, then it would actually get even larger. So here I have to do multiply by aspect. All right, so let's see what that does. Let me move my... that didn't do anything, obviously, because I have to add it over here as well now. So scale x and scale y. And also I have to restart. So I'm zoomed in again, so let me zoom out. And let's play around with this. And now you see that my fractal is always, or is never stretched. So great. All right, so what is the next thing? Actually, let me first put this into its own, this whole thing into its own function. Organize it a little bit. So private void update shader. And then I'm gonna stick this whole bunch of stuff, copy it or cut it and paste it over here. And now I'm going to say update shader over here. Update shader. And now this happens for every frame, right? The first thing I want to do is I want to do this for every fixed frame. So fixed update, the difference between fixed update and update is that fixed update will execute a fixed number of times per second, as opposed to update, which updates depending on how fast your computer is, which is not what you want. So before I do the update shader, I'm going to handle my inputs, or the user inputs, because we're going to have the user input use keys to move the fractal around. So I'm gonna make a private function for that as well. So private void handle input. And then the first thing that we're going to do is we're going to have keys for zooming in and zooming out. And for me, I'm going to put that on the keypad. So if input dot get key and then key code dot let's make the zoom in on the keypad plus. If you have a laptop and you don't have a keypad, then obviously you have to put it on something else. So we could say scale. Well, the naive way of doing it would be just saying scale minus equals and then some small value. But that is wrong, because if we do this, then our scale is going to get smaller by the same amount each time. And we don't really want that, because as we get zoomed in more, we can't have the scale go down by an equal amount, because then it will look like you're zooming faster and faster. And if that isn't clear, then maybe it would be clear to you that this, if we just do this, then our scale can get smaller than 0. It will not go to 0, it will just go through 0 and it will go negative, which is obviously not what we want. So we have to make this scale proportional to itself. So instead of using a minus here, I'm just going to multiply, and I'm going to multiply by some number that is slightly smaller than 1. So what this does is it will just reduce it percentage-wise. So each time it gets here, scale will get 1% smaller. And so this will make it that scale can never get to 0, and it can never get on the other side of 0, which is what we want. So I'm going to copy this, and I'm going to do the same thing for the keypad minus. And for minus, we want to set just on the other side of 1. So let's say 1.01. Let's see what that does. So save this. I have to restart this. And actually, before I do that, because this is annoying, let me just make it that it always starts at 2. Okay, there we go. And now if I press the plus on the keypad, it will zoom in, and minus it will zoom out. And if we go up to some more interesting spot on the fractal, we can see that it will zoom in, but it will never get to 0, which is what we want. And also it's proportional, so the zoom seems to go at the same speed every time, which is exactly what we want. All right, now let's do the movement. So I'm just going to copy one of these here. And for the movement, I'm going to use the AWSD keys on the keyboard. So A would be left. So there we go. And we just take the X position of the position, or well, the X position, and do minus equals. And this also has to be proportional. This is proportional to the scale, so I can just multiply this by the scale, so that if we're all the way zoomed in and scale is very, very, very small, then this number will be very, very, very small. So that should work. So let me just do this and copy this for the other side. So the other side would be D to go right. Let me just test this real quick before we go too far. All right, and now if I press A, if I press D, it goes right. If I press A, it goes left. Awesome. So same thing, obviously, for up and down. Copy paste this whole thing, and I'm gonna go down first, which is S, and up is W, and then I have to obviously change the Y position over here. All right, so now I should have something where I can go all the way around and I can zoom in wherever I want, which is awesome. Let's find a nice spiral. Wow, that's amazing. All right, so now what I want to do is, this is great, but I would like to add some momentum to my movement. So because right now, if I stop pressing my buttons, it stops right away. And wouldn't it be cool if it just slid off a little bit? It doesn't stop right away. And there is a really easy way to do that. That's very powerful, and I use in many different places. So let's use that here. So what I'm going to do is I'm going to make a private vector2, and I'm going to call it smooth pause. And I'm going to make a private float, and I call it smooth scale. And now what I'm going to do in my update shader, before I do any of this stuff, I'm going to say smooth pause equals vector2.lerp, which is an interpolation function that can interpolate between two different vectors. And the vectors I'm going to put in there is the original smooth pause and my non-smooth position. And let's say with a number 0.5. And what this is going to do is each time it gets in here, it will update smooth pause to be 50% closer to the non-smooth pause. So if this is my non-smooth pause and this is my smooth pause, then the first time we get in here, this smooth pause is going to be updated to be halfway between. So it's going to go over here. And the second time it's going to go halfway between the remaining distance. So it's going to be over here and then over here and then over here. And then if the original pause is moving, what's going to happen is that my smooth pause is just going to try to follow the original pause. And then when the original pause stops, then the smooth pause is going to catch up with it. So now this number is way too large. This was just for demonstration purposes. So generally you want to be under 0.1. So I'm just going to do 0.03. You can play around with this. And I'm going to do the same thing for my smooth scale. So smooth scale equals, and here it's in a different class because it's a float. So I have to do mathf lerp. And the same thing over here. So smooth scale, and then let's use the same number. Okay. And now what I'm going to do is every time here it says scale, I'm just going to replace that by smooth scale. And every time it says pause, I'm going to replace it by smooth pause. And now let's see what that does. Press play. And now you see already that it zoomed out to the original position. And now if I move around and I stop pressing my button, you can see that it slowly comes to a halt. And the same thing with zoom in and zoom out. So I stop pressing my button now, and you see it just slowly slides to a halt, which is pretty cool. All right. The last thing that I'm going to do is I'm going to add a rotate function to this so that we can twist into the fractal if you want. So for that, let's go back to the shader and let me just write out the function used to rotate a point in 2D space. And I'm gonna just run through this. If you guys want a more in-depth video about exactly how this works, let me know in the comments below. But for now, let me just run through it. So I'm gonna, in my rod function, I'm gonna put a original point in there. I'm gonna put a pivot in there, which is the point around which we want to rotate, which is also a float 2. And then I'm gonna put an angle in there. And then what I'm going to do is I am going to, first of all, I'm going to subtract the pivot from the point so that now my pivot is at 0, 0. And now I'm going to go, my new P is my old P. And I'm going to go P dot X. Actually, I forgot one thing. Let me first get the sine and the cosine of the angle. So S is the sine of my angle, C is the cosine of my angle. All right, and now we get here. So now what I'm going to say is my new position is the P dot X times the cosine minus P dot Y times the sine. And then for the new Y, it's going to be P dot X times the sine plus P dot Y times the cosine. So that is how you rotate a point in 2D. And then once we're done with the rotation, we have to shift it back to the original pivot. So P plus equals pivot. And now we can just return our point P. Great. So now what we can do is over here we can say C equals rot C, comma, and my pivot is the middle of the screen, which is area.xy. And then I have to put in an angle. And the angle is something that I'm going to expose. So I'm going to go over here. I'm going to float angle. And then I have to also put it in my properties over here. So I'm going to go over there, angle, angle. And then my angle is in radians, and it's going to go from minus pi to 2, from minus pi to pi. So range minus pi to pi. And my default angle is going to be 0. So let's see what that does. Save this, go over here. And now let's go to my material over here. And now I have an angle slider. And now if I slide that, it rotates the fractal. Awesome. All right, so let's go back to the Explorer script and let's implement this. So I'm going to go here. I'm going to add a smooth angle already because we're going to smooth the angle as well. And then over here, I'm going to add an angle. And then we just have to do exactly the same thing as what we did for the scale. So over here, change that, change this angle, change my angle over here, angle, and now I have to, let me just go back here, and I have to set this individually. So set float angle, and then I'm gonna put my smooth angle in here, smooth angle. All right, and now I go to my inputs, and I'm going to just copy what I did for the scale. And then I'm going to put these on the keys that are just above AWSD, so the Q and the E key. So Q over here, and E over here, and then over here I'm going to add to my angle or subtract from my angle. So in this case, subtract. And the angle is one of those things that isn't dependent on the scale, so that's great. So we can just go minus some small number, and over here plus some small number. Angle plus some small number. All right, let's see what that does. So save, press play. Okay, so if I press E, it turns, well, the wrong direction, and if I press Q, it also turns the wrong direction, but it turns, so that's good. So that means we just have to turn the Q and the E around. So let's go over here, E and Q. And now it seems like we're done. But we're not, because, so yeah, if I press E, okay, it goes this way, Q goes the other way. But if I am at 0 rotation and I press D to go right, it goes right, and I press A and it goes left. But if I rotate, let's say by 90 degrees, you will notice that now if I press D, it will go up and down if I press A, which is kind of a bummer. So we have to get rid of that. It's because my original moving code here doesn't account for that angle. So we need to do that. So how do we do that? Well, a different way of writing this here is I could do this. I could do vector2 dir equals new vector2. And let's just define the x direction. So normally the x direction would be this, right? 1, 0. And in this case, because we're not moving by 1, but we're moving by this much. So let's just put this in. All right. So that would be the x direction. So if we just get rid of the y for 1 second, and just look at the X. So another way of writing this is instead of adding just to the X component of my vector, I can add to the entire vector this dir value, right? Because my Y component is 0 anyway, so if I add 0, that's not going to change anything. So this is going to work just as well as the other code is. And just to demonstrate that, go over here, press play. If I press D, it still goes right, and it still goes left if I press A. Awesome. So now what I can do is, if I go into my Mandelbrot shader here, and you see how I did this rotation over here, well, now I can do the same rotation on my dir over here. So let's do that. So we have to make an S for the sine of the angle, right? So I go here and I do S equals math f dot sine of the smooth angle. No, I'm going to do it of the angle. And I'm going to do the same thing for my C. So math f dot cosine of the angle. And now over here I can say my new dir, my rotated direction is new vector 2. And then I'm going to do the same thing as what I did in the shader. So I'm going to do dir dot x times cosine minus dir dot y times sine. And then over here I'm going to do dir dot x times sine plus dir dot y times cosine. Yeah, I hope I did that correct. Well, let's see. So let's save this. Press play. Okay, right and left still works. Now if I rotate 90 degrees, then right and left still works. Yay! Awesome. So now we have to do the same thing for the Y direction. So let's take the Y comments out. So I'm going to go over here, do that, and then here I'm just going to do minus dir and plus dir. And now obviously this direction is different. It's 90 degrees rotated from the direction for the X. So for that I'm just going to do this new vector 2. I'm going to swap around the coordinates, so dir dot y comma dir dot x, and I'm going to make this one negative. And that's just how this turned out to be to rotate 90 degrees. So let's check that. Up, down, left, right works, rotate works, and now if I press up and down it still goes in the right direction, and left and right. Awesome. Alright, one last little thing here is that I use the entire rotation formula over here, which I don't really have to do because for my start direction my Y component is going to be 0 anyways. So some of these terms will fall out of the equation. So if I go, yeah, so this dir y is 0, right? So this whole thing will be 0, so I can just get rid of this. And the same thing over here. So this should be the same thing. So let me just check if that's correct. Moving, rotating, and I can still move around. Awesome. So let's put this in full screen and admire this for a second. Actually, so I gotta go maximize on play, press play, and there we go. So that's our shader. Let's zoom into something cool. Let's go over here and find a cool spot and rotate. Awesome. So if you thought this was cool, great, but stick around because it can get a whole lot cooler, I promise. See you next time.